Welcome students to the Objective 2 Force video. In this force video we're going to focus on Newton's three laws, and just to get us started I want to share a short introduction of Newton's three laws. You don't have to write anything just yet or answer the essential questions in your matrix. There'll be plenty of time to do that as we move further into the video, and I'll go through some slides with some definitions and things that will help you answer those essential questions. But for now, let's take a look at this short video on Newton's three laws.
Ever notice that it's harder to start pedaling your bicycle than it is to ride at a constant speed? Or wondered what causes your bicycle to move? Or thought about why it goes forward instead of backwards or sideways? Perhaps not, and you wouldn't be alone. It wasn't until the 17th century that Isaac Newton described the fundamental laws of motion, and we understood the answer to these three questions. What Newton recognized was that things tend to keep on doing what they are already doing. So when your bicycle is stopped, it stays stopped, and when it is going, it stays going. Objects in motion tend to stay in motion, and objects at rest tend to stay at rest. That's Newton's first law. Physicists call it the law of inertia, which is a fancy way of saying that moving objects don't spontaneously speed up, slow down, or change direction. It is this inertia that you must overcome to get your bicycle moving. Now you know that you have to overcome inertia to get your bicycle moving, but what is it that allows you to overcome it? Well, the answer is explained by Newton's second law. In mathematical terms, Newton's second law says that force is the product of mass times acceleration. To cause an object to accelerate or speed up, a force must be applied. The more force you apply, the quicker you accelerate. And the more mass your bicycle has, and the more mass you have too, the more force you have to use to accelerate at the same rate. This is why it would be really difficult to pedal a 10,000-pound bicycle. And it is this force, which is applied by your legs pushing down on the pedals, that allows you to overcome Newton's law of inertia. The harder you push down on the pedals, the bigger the force, and the quicker you accelerate. Now on to the final question. When you do get your bike moving, why does it go forward? According to Newton's third law, for every action there is an equal and opposite reaction. To understand this, think about what happens when you drop a bouncy ball. As the bouncy ball hits the floor, it causes a downward force on the floor. This is the action. The floor reacts by pushing on the ball with the same force, but in the opposite direction, upward, causing it to bounce back up to you. Together, the floor and the ball form what's called the action-reaction pair. When it comes to your bicycle, it is a little more complicated. As your bicycle wheels spin clockwise, the parts of each tire touching the ground push backwards against the earth. The actions. The ground pushes forward with the same force against each of your tires. The reactions. Since you have two bicycle tires, each one forms an action-reaction pair with the ground. And since the earth is really, really, really big compared to your bicycle, it barely moves from the force caused by your bicycle tires pushing backwards. But you are propelled forward.
Well, I hope you enjoyed that brief introduction to Newton's three laws. Now I want to make sure you get your matrix out, make sure you see those essential questions, because we're going to jump right in there to kind of go a little bit deeper with Newton's three laws. So you'll want to be answering those essential questions in your on your Wix. And so we're going to go ahead and get started with Newton's first law, aka or also known as the law of inertia. And Newton's first law of motion states the following: that an object at rest will remain at rest, and an object in motion will remain in motion unless acted upon by an unbalanced force. So what that's saying is, if you have an object that is not moving, it is not going to start moving unless it's acted upon by an unbalanced force. And likewise, if you have an object that's in motion, it's going to keep on moving until an unbalanced force is acted upon it. Now, I've got a real-life example I want to show you in a short video clip of my son Caleb on a skateboard. So check this out.
An object at rest stays at rest. An object in motion remains in motion unless acted upon by an unbalanced force. Go, Caleb. Good job.
Yeah. So, kind of funny, but as you can see, Caleb and the skateboard would have remained at rest if Caleb hadn't applied an unbalanced force pushing off with his foot to get him and the skateboard moving forward. They just would have remained at rest because the law says, Newton's first law says that an object at rest will remain at rest unless it's acted upon by an unbalanced force. And then you also saw the second part of this law in action. When the skateboard hit the tire provided an unbalanced force that stopped the skateboard, but Caleb's inertia kept him moving over the skateboard and into the yard. Why? Because an object that's in motion will remain in motion unless it's acted upon by an unbalanced force. So the tire wasn't providing the unbalanced force on Caleb, just his skateboard, which is why we ought to be wearing our seatbelts. Guys, you look at the cartoon below and you'll see that guy's car hitting the brick wall, stops his car, but the man's inertia wants to keep him moving forward. So it's the same principle. And so that is Newton's first law, the law of inertia. Okay, so let's take a look at Newton's second law of motion, also known as the law of acceleration. The law of acceleration, or Newton's second law, states that the acceleration of an object, that's how fast you can speed an object up, depends heavily on the size of the force applied and the mass of the object itself. And in fact, there's a formula that goes with this law, and it's that force, which is measured in newtons, equals the mass of an object times its acceleration. That is to say, the more mass you have, the more force that object has. The more acceleration an object has, the more force that object can have. And so we have this formula, force equals mass times acceleration, or force equals ma. In the cartoon you see to the right, you have an elephant and you have a mouse falling from a building. And you wonder, they're falling at the same rate. And the reason they're falling at the same rate is because the force of gravity is 9.8 newtons. It's pulling on them at the same rate. So they're accelerating exactly the same, the force, the mouse and the elephant, as they move towards the ground. However, one of them has more force, not because of its acceleration, because the acceleration due to gravity is equal on both of them. They're hitting the ground at the exact same time. But the elephant has much more mass. So when it hits the ground, the elephant hits the ground with more force because it has more mass. I've got a real life example you just got to see. I have my second son Adam and my younger son Caleb that you met earlier, and I want you to check out this short video clip, because what I did was I had them run at one another. Adam has more mass than Caleb, and I just want you to see the result of that. So here we go.
On your mark, get set, go!
So the idea there, and that was kind of funny, the idea there is we tried to have both boys accelerate at approximately the same rate. Of course, it wasn't perfect. It's hard to do that in real life, but we tried to do about the same acceleration. And of course, Adam kills Caleb, knocks him across the yard. Why? Because he had more mass. The amount of mass an object has gives that object more force as it accelerates. But at the same time, it takes much more force to get Adam going because he has more mass. The acceleration of an object, again, depends on the size of the force applied and the mass itself. Now, I've got another video of a fighter that I want you to see. And this is one of Caleb's friends that works out at his gyms. And I want you to see that as the fighter increases the force, he increases the acceleration of the bag that he's punching on. So check this out.
All right. Go.
So as you can see, as Brendan applied more force, it increased the acceleration of the bag. In fact, the punching bag, when he really increased that force, moved completely off the screen. And again, that's because the acceleration of that bag depended upon the size of the force that Brendan was applying. And so as he increased his force, he increased the acceleration. If the bag had been heavier, it would have required even more force to get it to move. So, hope you enjoyed that example of Newton's second law of motion in action. All right, guys, now you probably saw this coming when I first introduced the formula associated with Newton's second law of motion, the law of acceleration, that we're going to have to solve some force problems. Again, the formula for force is force measured in newtons equals mass times acceleration, or F equals ma. So we're going to use this formula, force equals mass times acceleration, and I want to walk you through about 3 problems. So I'm going to switch over to the Ladybug for a second, and I'm going to walk you through 3 problems. We're going to solve for force, we're going to solve for mass, and we're going to solve for acceleration. So let's switch over to the Ladybug and work these problems out. Here we go. Alright guys, we've switched over to the Ladybug now, and we're going to work on solving 3 different force problems. Of course, our formula is down here in the bottom right of the page. Force equals mass times acceleration. One of our problems, this first one, we're going to solve for force, we're going to solve for mass, and we're going to solve for acceleration. And as with all of our problems and calculations in 8th grade science, we have a process we like to use. So we're going to work through that process to solve for force on this first problem. The first thing we want to do is we want to read the problem, and we want to write down what we know and what we don't know. Do we know force? Do we know mass? Do we know acceleration? So let's read the problem and figure out what we know and don't know. A girl on a scooter is accelerating at 2 meters per second squared. If the girl has a mass of 50 kilograms, how much force is acting on that girl? So let's go ahead and figure out what we know and don't know. First of all, it says that she's on a scooter and she's accelerating at 2 meters per second squared. So we know that we have acceleration, 2 meters per second squared. And by the way, this meters per second squared is our unit of measure for acceleration. We also know that the girl has a mass of 50 kilograms. Typically these problems will be, the mass will be in kilograms. And then of course we don't know what the force is, and so we're going to have to solve for force. So now it's time to plug and chug our numbers. So let's go ahead and write out our problem. We don't know force. Force equals mass, which is 50 kilograms, times acceleration, which is 2 meters per second squared. So we're just simply going to multiply 50 times 2, which gives us a force of 50 times 2, 100, and of course we measure force in newtons. And that's how we solve for force. Alright, let's move on to the next problem. In our next problem, we're going to solve for mass. So again, formula, but we're going to focus on solving for mass. So let's read the problem and let's figure out what we know and what we don't know. A model rocket is accelerating at a rate of 3 meters per second. That would probably, 3 meters per second is the same thing as saying 3 meters per second squared. That's probably the better way to say it. And so with a force of 1 Newton. What's the mass of the rocket? So what do we know? We have a force, 1 Newton. We have an acceleration, 3 meters per second squared. But we don't know the mass. So just like before, we're going to plug our numbers into the formula and solve for mass. So our force equals 1 Newton equals mass, which we don't know, times acceleration, which is 3 meters per second squared. Now, in order to solve for mass, we have to get mass by itself. And in order to do that, we're going to have to use an opposite operation. So we're looking at the problem, 1 Newton equals mass times 3 meters per second squared. How are we going to get mass by itself? Well, if it's multiplication, then the opposite operation would be to divide. So I'm going to divide by 3 meters per second squared. And of course 3 divided by 3 is 1, which allows us to cancel those out, leaving m by itself on this side of the equation. Now, we also know one of our rules in solving equations is whatever we do to one side of the equal sign, we have to do to the other. So if I divided by 3 here, I have to divide by 3 on this side of the equation. So 1 divided by 3. Now, how are we going to solve that? I'm going to set up a division problem. 1 divided by 3. It is possible to divide by a smaller or a larger number. And so, but the problem is 3 won't go into 1, so I'm going to have to put a decimal place, add a 0. When I put the decimal place, it allows me to add a 0. 3 will go into 10 3 times. So 3 times 3 is 9, leaving me with 1 again. What are we going to do about this? Well, if I add another decimal place here, I can add a 0. I can add a 0. 3 will go into 10 3 times. 3 times 3 is 9, leaving us 1 again. Can you get the feeling this is going to happen over and over again? So our answer is going to be 0.33. Our mass equals 0.33 kilograms, and that 0.33 is repeating, and we'll stop always at 2 decimal places. Okay, so that is how we solve for mass. Let's go ahead now and solve one final problem for acceleration. Now, again, we're going to read the problem, figure out what we know and what we don't know. Sam pulls a wheeled backpack with a force of 3 newtons. If the backpack has a mass of 6 kilograms, what is its acceleration? Now, the force is 3 newtons, always measured in newtons. Our mass is 6 kilograms. And our acceleration is what we don't know. We're going to try to figure out what the acceleration is. So let's set up our problem. 3 newtons is our force equals mass, 6 kilograms, times acceleration. Just like we did for mass, in order to solve for acceleration, we have to get it by itself. And in order to get it by itself, we're going to have to do the opposite operation. So we're going to, this is 6 times a, so the opposite would be dividing. So I'm going to divide by 6. And when I do, 6 divided by 6 is 1. It allows me to cancel these out, getting a by itself. But remember, whatever we do to one side of the equal sign, we have to do to the opposite. So now our equation is 3 newtons divided by 6 kilograms equals a. 3 divided by 6. What's that problem going to look like? 3 divided by 6. 6 will go into, it won't go into 3. So what are we going to do? Well, we've got to add a decimal point. It allows us to add a 0. Now, will 6 go into 30? It sure will. 5 times. And 5 times 6 is 30. And that's the end of that problem. 0.5. Acceleration, again, is measured in meters per second squared. So our acceleration equals 0.5 meters per second squared. And that is how we solve for acceleration. Alright, you can guarantee we're going to see some of these force problems in the not too distant future. Thank you.
Alright, so we're going to move into Newton's third law of motion, also known as the law of action and reaction. And Newton's third law of motion is defined as for every action there is an opposite and equal reaction. That is to say, when an object places a force onto another object, that force is returned in equal amounts, much like in the case of a rocket ship. When a rocket ship engines fire, there is a force that the engines put on the launching pad or on the ground. And when that happens, the ground or the launching pad applies that force back onto the rocket that propels it up into the air and eventually out of the Earth's atmosphere. There's another example here of a man that jumps off a boat. As he jumps off the boat, he applies force to the boat as he pushes away. But the boat applies that force back onto the man, which allows him to jump off the dock. And you can see the equal and opposite reaction, because not only does the man move forward, but the boat also moves backward. Now, to more clearly illustrate this, our own Miss Timmons is going to show you another example of equal and opposite reaction. Check this out.
Go, Miss Timmons. Jump. Wait. Let's get a picture of your feet. One more. Give me a trick.
So again, that's another great example of one of Newton's laws in action, Newton's third law. As Miss Timmons placed a force on the trampoline, that force was applied back to Miss Timmons in equal amount, and that's what allowed Miss Timmons to fly into the air. That's how trampolines work. They depend on Newton's third law of motion, the law of action and reaction. And that is it for Newton's 3 laws of motion. We will see you back in class. Make sure you complete your WICS answering all of the essential questions, and we'll discuss them further in class when we meet again. So this is Mr. B. I'll check you later.